This podcast introduces the listener to the application of advanced mathematics in Industry 6.0, which can be considered as the artificial intelligence genius that has escaped from the bottle, and there is no turning back for this genius. Industry 6.0 is completely changing the mathematical modeling of artificial intelligence. Now we are talking about living industrial ecosystems and orchestration of cognitive robot swarms. These two terms are new to most people, including scientists, although they go back at least 15 years. My name is Ada.
And mine, Jefferson. The podcast is an informal conversation, one of several on the state of the art of mathematical modeling. We hope you like it and that you are interested. Let's see, for decades, artificial intelligence has been fascinating. I would almost say obsessed with generative models and pattern recognition.
Of course, yes, absolutely.
And it makes perfect sense because it's visually stunning. But for optimization engineers, this kind of black box leaves a huge void.
An exact operational vacuum.
You need to automate millimetric operational decisions. You have to solve very complex systems of equations to prevent the entire value chain from collapsing.
I totally agree with that. Because modern industry, let's say, can't depend on systems that simply warn you about what has already happened or that estimate what could probably happen.
Need action.
Exactly. You need architecture that acts in a prescriptive and purely mathematical way to stabilize the operation in real time.
And that's where the famous Industry 6.0 paradigm comes in.
That's right. It's a tremendous conceptual leap. Not only does it improve what is there, but it redefines decision engineering under uncertainty.
And well, that's precisely the core mission of our dive today. We're going to break down layer by layer. All this is algorithmic and mathematical architecture. But I want to make something very, very clear from the beginning.
Go ahead.
All this in-depth analysis that we are doing today serves as the theoretical foundation. It is the technical preparation for that podcast that is going to be made soon.
Oh, of course, the session on Industry 6.0.
Exactly. In that podcast, all of this will be discussed in more depth, but focused on optimal supply chain planning. So today we are building the engine. And in that podcast, we'll see him race on the track.
It seems to me a perfect structure.
So for those who design software architecture, prepare your notes, because we're going to open the hood of this system.
Well, to understand how Industry 6.0 solves this stochastic uncertainty, we first have to look at neurobiology in a slightly unexpected way.
Wait a minute, in neurobiology?
Yes, this helps us understand why traditional information systems, the famous corporate ERP, fail so resoundingly when there is high entropy.
Let's see. Can you explain to me why we are mixing neurobiology with business software?
Because if you think about it, biology has been solving optimization problems under uncertainty for millions of years.
Good point.
In the central nervous system, we have a structure called the thalamus. The biological thalamus is, in essence, a passive sensory relay station.
In other words, it only receives data.
Exactly. It receives external data, classifies it, and sends it to the cerebral cortex. Corporate ERP systems fulfill exactly that same function.
They are thalamic systems, let's say.
Just like that. They absorb millions of transactions per second, store them neatly in relational databases, and show them to you in a very good dashboard.
Of course, the famous dashboard.
But if there's a serious disruption in your supply chain, ERP alone doesn't stabilize anything in the operation.
No, of course it doesn't just document the disaster in real time.
Exactly.
It's like, let's see. It's the perfect analogy for an airplane's black box.
Oops, I like that analogy.
Of course, the black box impeccably records all the physical parameters which, if the altitude, pressure, and telemetry of the engine, explains it in amazing detail. But why did the plane crash?
Yes.
But it does not execute any action on the ailerons to avoid the impact. It doesn't save you.
Exactly. Neurobiology, on the other hand, has the hypothalamus. This is the supreme commander of the homeostasis of internal balance. If your body perceives a drastic drop in temperature, the hypothalamus does not stay there registering the cold, and that's it.
No, of course. It makes you tremble.
It alters blood flow, orders muscles to shiver, generates thermal energy, and if we translate this into software engineering, we come across this revolutionary concept, the organizational mathematical hypothalamus.
Wow. But wait, it's important to clarify something here for the machine learning engineers listening to us.
Yes, tell me.
We're not talking about a classic neural network, are we? Because a traditional neural network uses super simple activation functions.
Like a sigmoid or a clear ReLU.
Exactly, that they propagate a value if you exceed a numerical threshold, and to see a ReLU, it is perfect for you to classify if there is a cat in a photo.
Yes, but it does not solve equality restrictions.
Exactly. It does not do a stoichiometric mass balance in a factory.
It's a critical distinction that you make. The mathematical hypothalamus uses a distributed network of complete optimization models. These models act like this incredibly complex mathematical neurons.
In other words, each node is a model in itself.
Yes, whether it's the inventory module, silo management, transportation, each one is a neuron. And what they exchange in real time are not simple binary impulses.
What do they exchange then?
They exchange primal and dual variables, all with the aim of achieving this homeostasis that in operations research is to maintain the minimum cost balance in the face of any disruption.
Continuing with the airplane, this mathematical hypothalamus would be like an ultra-high-precision autopilot.
Exactly.
He doesn't just read that there is a headwind. It recalculates the trajectory, alters altitude, and adjusts fuel in milliseconds, and uses dual variables to keep flight stable.
It's a brilliant concept, really.
It is, but here I have to put on the hat of a skeptical engineer.
Let's see you put the model to the test.
Solving mixed integer linear programming problems with MIP models in real time. That is computationally unfeasible.
Yes, we are talking about problems. MP hard.
Exactly. If you have 10,000 sensors or more, sending fluctuations per second, and the system tries to recalculate everything from scratch every time a piece of data arrives.
The servers are going to thermally collapse.
Yes, the clusters literally catch fire. How do they avoid that?
Well, that has been the historical barrier, and the solution proposed by Industry 5.0 is once again inspired by biology. With the artificial hippocampus.
Let's see. Explain that to me.
If the hypothalamus makes the decisions, the hippocampus functions as the long-term geometric memory of the system.
Geometric memory sounds advanced.
The key algorithmic breakthrough here is that, in the face of a new sensor disturbance, the system never starts calculating from scratch.
I understand the concept of memorization in dynamic programming. You save the result of an expensive function, and if the inputs are repeated, then you don't recalculate.
Yes, it is the standard.
But here we are talking about multidimensional polyhedra and exogenous stochastic variables. That is, the inputs of temperature or demand are almost never going to be repeated with decimal precision.
It is never statistically impossible.
So, what good is it for you to keep the memory of a state that is not going to happen again in an identical way?
That's the million-dollar question, and the answer is that we're not maintaining specific solutions.
What do they keep then?
What this artificial hippocampus stores are the geometric structures that mathematical solvers discovered in past iterations.
Ouch.
Specifically, it stores cutting planes and approximations of convex hulls.
I already understand the mechanism. Instead of memorizing the exact answer to a point, they memorize the mathematical boundaries.
Exactly.
They hold information that indicates that we have already explored this region of multidimensional space, and we know with mathematical certainty that the optimal solution is not here, or if it is.
You synthesized it perfectly. By retrieving these polyhedral structures from the database, the system instantly prunes gigantic areas of the space from non-integer solutions.
Of course, you save yourself all that calculation.
In this way, we avoid the commercial solvers, for example Cplex, which runs a branch and bound algorithm, the immersed effort of exploring useless branches in the search tree.
Is it? How to prune the dead branches of a giant maze before you even start running through it?
Exactly. This geometric pruning reduces the effort dramatically, and that is what enables the almost instantaneous response.
Ready, that explains the how of speed. We have the architecture and the memory. Now let's open the algorithmic engine. How are these equations structured?
Well, the core is based on a recursive structure specifically for multi-period stochastic optimization.
It sounds dense.
A little. In algebra, We see it as a function of the value of the objective function at time t. This function depends on the previous state.
Let's break this down so we don't lose anyone. The variable x and t would represent our current operational decisions, right?
Correct, like how much inventory to move or which machine to turn on today.
Would y be for the marginal costs associated with those decisions? All this, adjusted for a beta factor, that I understand is the temporal discount rate.
That's all the way it is. That's the deterministic, classic part, but the real algorithmic monster is the variable nt.
The stochastic vector.
That's right. It's the multivariate random vector of perturbations. It represents pure volatility, market prices, mechanical failures, weather shocks.
It is the entropy of the physical world injected into mathematics.
Just like that. And the goal of this recursive function is to minimize today's operating costs added to the expected value of future costs. Under all that uncertainty.
But trying to solve such an equation for an entire corporation in a single block is ram suicide.
Absolutely. That is why large-scale parallel decomposition architectures are used.
Such as generalized Bender's decomposition or generalized dual dynamic programming, GP.
The GDDP does. And its stochastic variant, the GSDDP.
And here I have to raise another huge red flag, the famous curse of dimensionality.
Thus, the terror of optimization.
Because if the GSDDP incorporates that multivariate uncertainty, the trees of scenarios that unfold into the future, the combinatorial growth suffocates the model.
Yes, in a high volatility event you run out of memory.
So how do they avoid collapsing by calculating infinite possible futures?
It's a classic limitation, but GSDDP solves it in a super elegant way. The secret lies in the future value function.
Uh-huh.
The algorithm never tries to exhaustively evaluate each node of that scenario tree. It is impossible. What it does is iteratively use those. I talked about Bender's cutting planes.
To make an approximation, I imagine.
Exactly, construct an external approximation of that future value function.
I need to visualize this to see you telling me that they don't calculate the exact value of next Tuesday.
No.
Rather, they build a kind of geometric envelope that limits up and down. How much that could cost in the future.
It's an excellent visual analogy. Imagine you have a square block of clay and want to sculpt a perfect sphere in the center.
Okay, yes, I have the clay.
You don't try to calculate the position of each clay molecule in the center. You start making flat cuts from the outside. Pam, pam, pam.
Of course, you take away large pieces.
Each iteration adds a new cutoff plane that sculpts the function from the outside. With enough cuts, the approximation becomes incredibly precise, right in the region of the optimal decision.
And you achieve it without going through the entire tree of probabilistic scenarios. What a brutality of efficiency.
It is very beautiful mathematics.
Now these models always look infallible in a paper.
Of course, in theory everything works.
But the real litmus test is when you impose this math on living cyberphysical systems, where determinism does not exist at all. It is the principle of Industry 6.0.
And that is where the industry route comes in.
Exactly. And that's what corporate precision decision-making is for, which is like the ultimate high-entropy laboratory.
It is the most hostile and imaginable environment for deterministic optimization.
Because if you design the logistics of a car assembler, you control the cycle times in exact seconds.
But in agribusiness, we deal with biological organisms, ontogenic cycles that are irreversible.
And here let's take the example of agribusiness that serves us perfectly to understand the dynamics that we will discuss in the podcast that will be published soon.
Perfect. The cycle of agriculture varies depending on 1,000 things.
Now I'd like to talk more about Industry 6.0, but we've established that Industry 6.0 doesn't work like that. It is based on living industrial ecosystems and orchestration of cognitive robot swarms. If there's no dictator, how will all this be orchestrated?
Through distributed architecture, each industrial ecosystem operates as an autonomous IoT node.
Autonomous and independent.
It is achieved by exact consensus algorithms, and here comes a spectacular mathematical principle. The autonomous theory of the duality of the Lagrange.
Ugh! The multipliers of the Lagrange. If we take this to the network economy, These multipliers act as an internal price system.
It's an organizational currency exactly.
Let's see if I can illustrate it quickly. Let's assume that an industrial plant is at 99% of its capacity, about to explode.
Okay.
Its marginal cost triggers this Lagrange multiplier, which works as a mathematical penalty. It is transmitted asynchronously to the field.
It reaches the node of another facility, for example, a harvester.
Exactly. The harvester node receives that superinflated price signal, and its local algorithm decides that it is financially cheaper. Delay the harvest by 48 hours.
Instead of harvesting today and paying the immense penalty of sending rice to a collapsed plant.
It's amazing. It is a free market for transactional capacity.
Operating at millisecond scale, nodes negotiate, balance penalties, and reach an optimal global consensus. No node can maximize its throughput if it means crashing the network.
The theoretical beauty of this is undeniable. But here comes my headache as an engineer.
Let's see.
Formulate this by hand. Writing the code from scratch to couple the Lagrange with multi-scenario stochastic shear and decomposition planes is a software nightmare.
It's the worst bottleneck in the industry. You can spend 2 years just translating math into code for CPLX.
With syntax errors and memory overflows guaranteed.
That is why the practical deployment of all this is supported by a cognitive robot called Optex.
An expert system in optimization, right?
Yes, Optex is an integrated, super-intelligent development environment. It allows engineers to completely abstract themselves from the code.
In other words, the engineer only draws the logic of the business, eliminates human error in syntax. Every programmer's dream.
The math modeler defines the logical architecture and mathematical equations, and Optex generates all the source code autonomously.
It works as an ultra-high-level compiler.
Absolutely. And the best thing is that the code produced is agnostic. It natively supports IBM CPLEX, AMPL, MOSL, even C and Python. The crown.
But of course, if Optex generates 1 million lines of code where you run that monster, my laptop will melt.
To this end, the infrastructure was developed in a mathematical modeling as a service.
Cloud optimization.
That's right, it's a cloud-native architecture, deploying swarms of hybrid clusters, combining sequential CPU processing with raw GPU parallelization.
All working together.
And it integrates with math-oriented relational databases to move those arrays very quickly.
And I guess this democratizes technology.
That is the great revolution. Before, only an airline or an oil company, a large company, could pay for clusters like these. Today, an SME can rent these nodes as a service.
It is a monumental display, really.
It is.
Well, to sum up this super dense ride, we looked at how to replace the passive decision support system with a proactive mathematical hypothalamus.
With real decisions.
We understood that it needs a geometric memory, the artificial hippocampus keeping cutting planes, so as not to start from scratch.
That is very important.
We explore how the algorithm approximates the stochastic future, sculpting value functions from the outside.
We saw how Lagrange's theory of duality synchronizes industrial facilities as an internal market in the cloud.
It is, let's say, the pinnacle of Industry 6.0's prescriptive analytics, the ultimate tool against entropy. And all the engineers and system architects who have come together today to unravel these equations are invited to remember once again.
Yes, this is just the beginning.
Exactly. This entire theoretical framework is only the map, the practical, tactical, and economic profitability impact. We're going to see it in action during that podcast that is going to be made soon.
That's right.
That podcast will be dedicated to optimal chain planning. There we will see these dual variables negotiating between industrial facilities. And well, to close for today, I want to leave you all with a slightly provocative reflection.
Let's see what you come up with.
Analyze this from game theory and macroeconomics. If these algorithms based on Lagrange and geometric memory can synchronize the biology of a field and the thermodynamics of a factory, operating a perfect market within a corporation, that will happen with global macroeconomic dynamics. The day when the artificial hypothalamuses of competing firms inevitably begin to exchange marginal cost dual variables and to negotiate fully autonomously on the open market.
The market operated by algorithms to the millisecond, That changes everything, and it is typical of Industry 6.0.
Totally clear. I'll leave you with a worry. It's been a geek pleasure until our next analysis. We invite you to the next podcast, live in Spanish, which will take place on June 26th at 10 a.m. in Miami. The topic is planning of agro-industrial supply chains. Cordially,